Hello and welcome to the last part of Lecture 6 of Math 2R03. We've been talking about spanning sets and linearly independence, and we're ending today with kind of a theorem about finite dimensional vector spaces. And it says that every subspace of a finite dimensional vector space is also finite dimensional. So you may think, well, that seems kind of obvious, but of course we always should work out the details and make sure it's true. And we're going to use some of the results that we just proved in the previous section parts to verify that this fact is true. Okay, so let's talk about a proof. So let's say that we take a subspace. U will be any subspace of V. If it happens to be the trivial subspace, well then U is the span of 0, and this is actually finite dimensional, so we're done, right? So we're done here because it's a subspace that's finite dimensional. So now, on the other hand, let's suppose that we were unfortunate and we took a vector space U that properly contained 0, so it's not the trivial space, and U is not finite dimensional. Okay, so what does that mean? Well, that means that we can find U1 such that when you look at the span of U1, take U1 inside of U, and we look at the span of that, it can't be all of U. If it was all of U, then it would be finite dimensional. Okay, so that's good. And now for each j greater than or equal to 1, there has to be a uj inside of U minus the things that you've seen before. Okay, U1 up to uj minus 1. So think about this kind of step by step. So U doesn't equal the span of U1. So that means there has to be a vector that we haven't seen in U. We'll call it U2. And now look at the span of U1 and U2. Because U is not finite dimensional, it doesn't equal all of U, so you can find a new guy, a U3. All right, and so that's basically what we're doing. We're just kind of finding a vector that we haven't seen before in the span, adding it to the span, and at each step, because it's not finite dimensional, we can we can find a new vector we haven't seen before. Right, so we end up kind of with this sequence. We have a U2, which is not in the span of U1. You have a U3, which is not in the span of U1, U2. Then we would have U4 is not in the span of U1, U2, U3, and so on, right? And now because of this, and maybe I should also mention, note all U1, U2, U3, and so on are in U, which is contained in V. Right? So you're getting kind of this infinite sequence of vectors, U1, U2, U3, where each UI is not in the span of the thing that you've seen before. And because of that, by the independence lemma, we know that U1, U2, U3, and so on, you take this infinite list, is linearly independent. Okay, and why does that come from the independence lemma? Well, the independence lemma would say that if they were linearly dependent, at some point one of the UIs would show up in the span of the previous guys, but that's not what we have, right? Each of these UIs are picked to be outside of the span of the previous guys. Right? So you have U1, U2, U3 being a linearly independent set. Okay, so we have an infinite number of these guys, but on the other hand, V is finite dimensional. So a finite set spans V, right? And so now we have a contradiction. We now have a contradiction to the previous result, okay? And why is that? i.e., there is an infinite list of elements that are linearly independent, and there is a finite list of elements that span V. right? But why, just to kind of re-emphasize, why is this a contradiction? Well, look, oh, I have to go back 2 slides here. Why is this a contradiction? Well, it says that every list of linear independent vectors is less than or equal to the length of every spanning list. But here we have a list of vectors that is infinite in length, but a finite list of vectors that span V. So we get a contradiction, right? So U must be finite dimensional, which is what we wanted to prove at the beginning. Okay, so we want this to be a finite dimensional vector space. Okay, give you a second and a chance to read that. And moving to the next page here, just kind of like want to kind of talk about where we're going to go next and some of the key ideas from today's lecture. So in the next lecture, we're going to combine these 2 ideas. We're going to combine the notion of span and linear independence, and they get combined in the notion of what a basis is. So we're going to spend some time talking about bases of vector spaces in the next lecture. The key ideas from today's lecture are the notions of linear independence and dependence, and one of the kind of most useful results from today's lecture is the linear independence lemma. So we'll stop there, and I will see you in lecture 7. Have a great day.